Chemistry and the Aquarium, the relationship between alkalinity and pH, by Randy. Like the relationship between alkalinity and calcium, the relationship between alkalinity and pH takes many forms. One of the most important of these is simply that alkalinity is defined as the amount of acid necessary to change the pH of the sample to a specific value. Beyond that relationship, however, is where the interesting tidbits lie. How does atmospheric carbon dioxide impact pH in my tank? What is the relationship between alkalinity, supplementation, and pH? How does the alkalinity impact pH stability in brief tanks? What is a buffer and what does it have to do with alkalinity? This article will endeavor to clarify this relationship. The mathematical relationship between carbonate, alkali, and pH. It turns out that there is an exact mathematical relationship between pH and carbonate alkalinity for any aqueous system in equilibrium with the atmosphere. In this context, carbonate alkalinity is defined as the alkalinity provided by carbonate and bicarbonate, and does not include the minor contributions to alkalinity provided by borate, silicate, phosphate, hydroxide, and the negative contribution from protons. You saw this? In normal seawater at pH 8.0, the carbonate alkalinity accounts for 96.5% of total alkalinity. So for most purposes, the contributions from these other ions can be ignored. Two situations where they cannot be ignored, however, are when borate is artificially high, as is true in some commercial salt mix, and when one is considering the buffer intensity, where borate is significant even in normal seawater. They're going to discuss it below. Let's move on. Carbonate alkalinity, AC, is mathematically defined as AC equal Ds plus Ds. So this is bicarbonate and carbonate. Carbonate have two, where X means the concentration of species X. I think because of AC. Okay. Carbonate is counted twice because it contributes 2 units of alkalinity for each unit of concentration. The relationship between the amount of bicarbonate and carbonate to pH is well defined if the system is at equilibrium with the atmosphere. Substituting this known relationship into equation 1, we will get this. Okay, it's kind of a complicated equation where PCO2 is the concentration CO2 in the air. This current carbon dioxide concentrations are around 350 ppm and have been rising with time from less than 300 ppm in pre-industrial times. So yep. Okay. KH is the Henry's law constant for CO2, which describes the solubility of CO2 in water from the air to form carbonic acid. K1 is the first dissociation constant for carbonic acid. The first, okay, describing the dissociation of H2CO3 to HCO3 minus, which is carbonic acid to bicarbonate, and K2 is the second dissociation constant for carbonic acid, describing the dissonance so from bicarbonate to carbonate. It is not easy to look at equation 2, well, it's really complicated, and see any particular relationship between alkalinity and pH. But it is easy to see graphically using equation 2. Using equation 2 and 3, the definition of pH, we can plot the relationship graphically. Figure 1 is this. 3, this is the formula for pH. Okay, let's look at the graph first. The theoretical relationship between carbonate alkalinity and pH for seawater, blue, and fresh water, red, equilibrated with atmosphere CO2, 350 ppm, with using equation 2 and 3. Okay. Note that for purpose of this article, I am ignoring the fact that there are several different pH scales used in seawater that vary on the order of 0.1 to 0.2 pH units, and that activity coefficients are required to properly use such equations. These are fascinating ideas in and of themselves, and may be discussed in detail in future columns, but are unnecessary to understand the fundamental relationship between alkalinity and pH. There are two things readily apparent from figure 1. The first is that alkalinity rises sharply as pH rises. So pH, alkalinity rise, pH also rise. So when pH rises, alkalinity rises. Okay. This becomes especially true above pH 8 in salt water, where there becomes an appreciable concentration of carbonate. Why exactly is this true? Here's a simple non-quantitative way to think about it. Carbon dioxide has a specific solubility in water as carbonic acid. Regardless of pH, at a given salt concentration, this carbonic acid concentration is always the same. All that determines the concentration of carbonic acid is the amount of CO2 in the air. Further, at any given pH, there is an exact mathematical relationship between carbonic acid and both bicarbonate and carbonate. These relations are, in fact, those used to derive equation 2. The first term in equation 2 is bicarbonate, and the second term in equation 2 is carbonate. For example, at a pH of about 9.3 in freshwater, about 8.4 in seawater, the carbonate concentration is 100 times that of the carbonic acid. At higher pH, this multiplier rises, and there is consequently more bicarbonate and carbonate present. More bicarbonate and carbonate results in higher alkalinity, as is shown in figure 1. Yes. A second interesting feature of figure 1 is that at any pH, the alkalinity of seawater is much higher than that in freshwater, correct? Okay. The reason in simple terms is that the multipliers described above are larger in salt water. The more quantitative reason is that the dissociation constants are higher in salt water. Higher dissociation constant force a higher concentration of bicarbonate and carbonate to be present for a given concentration of carbonic acid. Hence, they result in a higher alkalinity. Higher. Okay. A third feature of this relationship involves the pH of seawater as the ambient CO2 level rises. Involves the pH of seawater as the ambient CO2 level rises. If CO2 is allowed to double, the pH drops by 0.3 pH units, assuming that the alkalinity is unchanged. Consequently, in the future, the pH of seawater may actually drop into the upper sevens from the 8.0 to 8.2 range present today. Let's move on. pH versus alkalinity in reef tanks. At the start of the last section, it was pointed out that there is an exact mathematical relationship between pH and carbonate alkalinity of any aqueous system in equilibrium with the atmosphere. An important point to keep in mind is that the relationship will be altered slightly if the tank is not in equilibrium with the air. Specifically, reef tanks are often not in equilibrium with the air, making the internal PCO2 for the tank something different than the surrounding air. For example, tank using lime water can have a pH value of 8.5 with a total alkalinity of only 3 MEQ per liter. Looking at figure 2, this put them off of the theoretical relationship for seawater in ambient air. The fundamental explanation is that the tank is deficient in CO2. In effect, the tank has an internal PCO2 that is more like that for the pre-industrial air with 273 ppm CO2. In this case, driving more CO2 from normal air into the water will lower the pH to about 8.2 to 8.3 while maintaining the same alkalinity. Okay, so the green is pre-industrial air, which is in pre-industrial era. Current one is blue, which is 350 ppm carbon dioxide. Future air is just future presumption. Okay. Likewise, tanks that use calcium carbonate carbon dioxide reactors often have a pH of 8.0 with an alkalinity of 3 MEq per liter or more. Again, that set of values falls off of the theoretical curve shown in figure 2. In this case, the tank has an artificially high internal PCO2 of more than twice normal air. Driving more CO2 from the tank into normal air will rise the pH to about 8.2 to 8.3 while maintaining the same alkalinity. Okay. So this scenario is driving more CO2 from the air into the water. This scenario is CO2 gassing out of the water into the atmosphere to equal it. Okay. A third way that reef tanks can present unusual combination of pH and alkalinity is if the tank is in an environment where the ambient CO2 is far from normal. Rarely will such a situation involve reduced CO2, but homes and businesses are frequently elevated with respect to CO2. Such levels as those represented by the 700 ppm line in figure 2 are frequently encountered by aquarists, especially those living in newer, tighter homes. And some have proven this fact to themselves with carbon dioxide detectors. Aquarists that experience chronic low pH despite adequate alkalinity and aeration may do so because their homes have such elevated levels of carbon dioxide. Many of these aquarists have found that the pH of their tanks rises substantially by simply leaving a window near the tank open to permit better exchange with exterior normal air. Finally, PCO2 fluctuates within a reef tank every day because of the activities of the organism present. Some are producing CO2 as a waste product of metabolism, including all organisms in the dark. Yes, reason like plant. So plant produce CO2 in the night and absorb CO2 in the day. Those that photosynthesize consume CO2 during a day. Yes. As a consequence, the PCO2 rises during the night and declines during the day. This change in PCO2 is largely responsible for the pH fluctuation over the course of a day. For all these reasons, a tank may move between red and green lines of figure 2 or further in extreme cases without the alkalinity changing at all. Typical durian pH fluctuations in a reef tank and in some natural lagoons for that matter are at about 0.1 to 0.3 pH units. For tank with a larger fluctuation than about 0.3 pH units, the aquarist might want to look for ways to minimize the fluctuation. This minimization is best accomplished by maximizing the gas exchange between the tank and normal air through better circulation, better aeration through devices such as skimmers, having part of the tank system such as a refugium on a reverse photocycle, so some organisms are always photosynthesizing, or by more rapidly exchanging the room air with exterior air. One can also impact the durian pH fluctuation by adding high pH additives like lime water or other high pH alkalinity additives during the nightly pH minimum, and by adding low pH additive like sodium bicarbonate during the daily pH maximum. The magnitude of alkalinity itself, of course, can influence pH stability, and that is the focus of the next section.